Welcome to the second part of magnetism. So far, we have looked at simple phenomenon of magnetism. In this video, we're going to take a look at electromagnetic effects. In the next video, we'll take a look at AC generators, and in the last video, we'll take a look at transformers. So in AC generators and transformers, we're going to use concepts from here and from here. So what is electromagnetic effect? So electromagnetic effect is basically about the interaction or the relation between magnetism and electricity. So we're going to start with what is called Fermi's left-hand rule. But before we can go into what this rule is all about, we have to describe or to define what electromagnetic effects are. So, if a wire is placed where a magnetic field is and a current flows in a wire, a force acts on the wire. You get a wire, you put it near a magnet. Remember, near a magnet there is a magnetic field. And if there is a current or electricity passing through that wire, then that wire is going to be pushed in a certain direction. So that's what electromagnetic effect is all about, the interaction between electricity and magnetism, which brings about these forces that end up pushing a wire in a certain direction. With that being said, the job now is to learn how to determine the direction. These principles are used to, for example, to generate electricity, as you are going to see when we are studying AC generators. So knowing where the force is going to be, because okay, let me just say that again. There are three I don't want to use the word forces, or there are three different concepts here. There is magnetism, electricity, and force. Okay, so magnetism, we're talking about magnetic field. We can tell the direction of the magnetic field. We can tell that it is moving from this to this just by knowing where the North Pole and the South Pole is. We can also tell the direction of current just by the way we connect the wires to the battery. But the direction of this force, which is introduced when a wire that is carrying current is placed around the magnetic field, is one that is difficult to tell. So to tell that direction, we need to use Fermi's left-hand rule. So if we have this situation, which I'm trying to describe, we have a magnet here and a magnet here. So the direction of the force, the direction of the magnetic field is from north to south. So it will be like this. Okay. Sometimes these these lines that represent magnetic field are called magnetic flux. Magnetic flux. So sometimes I'll be using the word magnetic flux to describe these lines. Okay. So if we have this arrangement, the direction of the magnetic flux is from north to south. Then let's say we have a wire and current is moving from here coming towards us. So it's moving from the screen coming towards us like this. So in this case, the direction of the current is towards us. Okay. Now, if you arrange like this, the direction of the force is going to be upwards. Okay. So this, since I've told you, it's easy. So long as you have this direction and this direction, you can tell. But what if we change the direction of the current from here to here? Or we change the direction of the force from here to here? I mean, the direction of the magnetic field from here to here. What will be the direction of the force? So to determine this direction, that's where Fermi's left-hand rule comes in. Remember, there's Fermi's right-hand rule, or the right-hand thumb rule, which we learned in magnetism, in the first part of magnetism, which is about determining where the North Pole is, depending on the direction of the current. But here, we're going to talk about Fermi's left-hand rule, which you use your left hand. So you have to arrange your fingers of your left hand like this. Okay? So this is your left hand. So the first thing that you should arrange is the first finger. It should point to where the magnetic field is pointing. This magnetic field is pointing from left to right. So this should be pointing to the right because that's where the magnetic field is going. Okay. Then after this, you have to arrange the second finger such that it is at 90 degrees. So in this case, this is pointing to the right. Then this finger should be pointing at you. As I'm explaining, try to follow me by arranging your fingers like this, like the way I've drawn here. So this finger should be pointing at you. So let me just say that again. I don't want to mislead you. This finger should be at 90 degrees to this one. Okay. Now, where should this finger point? What determines where this finger points is the direction of the current. So if the current is moving from here to here, then we can see that the current is coming towards us. So this finger should be pointing towards us. Okay. If the current is moving from here going inside, then you have to turn your, this should always be at 90 degrees, this and this. So you have to turn your left hand such that this point outwards, not towards you, but away from you. So in short, you have to turn your left hand upside down. From this position, you turn it upside down so that this points outwards or away from you, and you should be seeing the back of your hand. If you have done it properly, you should be seeing the back of your hand, not this part of your hand, okay, such that these two fingers should be hidden from your sight. Okay, so that's the first thing. The first finger should point where the magnetic field is pointing. The second finger should be pointing where the current is pointing. Then the thumb should also be at 90 degrees to the first finger. Okay, so in this case, which of course is this arrangement, the thumb should be pointing upwards. That's the way it can be nearly 90 degrees to the first finger. So where the thumb is pointing, that's where the force is going to be. That's why the force here is the same as the thumb here. Okay, so that is how to use Fleming's left hand rule. Let's say we change one parameter here. We change maybe the direction of the current. Let's say the current moves from here to here. Okay, so meaning that this finger should be pointing away from us. The only way you can achieve, if the fingers are arranged like this, the only way you can achieve the situation where this is pointing away from us is to turn this upside down, such that you should see the back of your hand and these two fingers should be hidden. So when you turn the left hand, you twist it such that it is upside down, this is going to point downwards, meaning that the direction of the force in such a case is downwards. Okay, let's try a third situation where we go back to this initial arrangement. Then we say the direction of the force we change, maybe of the north pole here and the south pole here. Then the direction of the magnetic field is from here to here, from right to left, meaning that this has to point to the left. So how can you turn this so that you point to the left? So what you can do for that to be possible, you right now I'm just trying to turn it so that I see how I can achieve that. So if you turn it, it's just that you have to turn it like this. It's hard to show since this is a 2D surface, but you have to turn it in such a way that this points this direction. So you have to twist it at 180 degrees so that it points to your left. Then this is going to point inwards also, and this is going to point upwards. Okay, so just make sure that now the issue is, if this points inwards, when we turn it 180 degrees, like for it to face this, then we turn it or we turn it right to left. Okay, this is going to point inwards instead of pointing outwards, because our current is pointing towards us. So it means we have wrongly arranged the fingers. This should point towards us, then this should point to the left. So the other way you can achieve that is if you turn this, if you turn your hand the way it is, you rotate it like this. Okay, so that this comes like this. It's going to be a little bit hard, but you have to push so that this points to the left, and this should still be pointing at you. Okay, you don't point exactly at you, but where you are. Again, you should be able to see this part of your hand, and the thumb is going to be downwards if you have done it properly. It's like you rotate it like this. This points this still remains pointing at you, and the thumb will be pointing downwards. Hope you have been able to follow. Yeah, but that's how to apply Fleming's left hand rule. Next, we're going to take a look at Faraday's law of electromagnetic induction. So Faraday's law of electromagnetic induction is all about induction of magnetism, or not okay, yes, induction of magnetism and electricity into something. Remember, when we're talking about charge, we talked about induced charge. Then when we're talking about magnetism, we talked about induced magnetism. Now we're talking about induced electromagnetism. So if any electrical conductor moves in the magnetic field and cut the magnetic flux, an EMF is induced in the conductor. So if there is a magnet somewhere, around the magnet there is a magnetic field. The lines of the magnetic field is what I'm referring to as magnetic flux. So if you have a wire that is capable of carrying electricity, then you move it across the magnetic flux. To move it across the magnetic flux, the other word we use is cutting the magnetic flux. So as you move that wire across the magnetic flux, we say it is cutting the magnetic flux. So when that is happening, there will be electricity in that wire, and that is how electricity is made. So this is called electromagnetic induction. The strength of the induced EMF is proportional to the rate of change of the magnetic flux. Okay, so the strength of this voltage which is introduced in that wire, or the current that is introduced in that wire, is proportional to how fast the magnetic flux are changing. By that, I mean how fast the wire is moving across the magnetic field, or how fast. Sometimes you can even keep the wire stationary, then you can be moving the magnet. Still, there will be that action of the wire moving across the magnetic field, even if it is the magnetic field that is moving across the wire. The effect or the impact is going to be the same. So, when they say change of the magnetic flux, it's how fast the wire is passing or is going across the field. So the strength of the induced voltage or current is proportional to how fast the magnetic field is being cut, or how fast the wire and the magnetic field are moving across. The simplest way to say that is the rate of change of the magnetic flux. So that law, which the law which relates the strength of the magnetic field, and also I mean the one that relates to the EMF to the strength of the, let me say that again, the law that relates the strength of the EMF to the rate of change of the magnetic flux is what is called Faraday's law of electromagnetic induction. So sorry for next we look at Lenz's law. This is going to be the last law we're going to take a look at. So Lenz's law comes from this observation. If a magnet, you get a magnet, you move it towards a solenoid. Remember, a solenoid, a coil, of course, it can even have a core in between, a coiled wire that might be surrounding another metal, maybe a soft magnetic material like iron. So if a magnet moves towards a solenoid, the solenoid makes a magnetic field which tends to repel it. Okay, so if you have a solenoid, then you have a magnet, then you are moving it towards the solenoid. The solenoid somehow will make a magnetic field that's going to repel that magnet that's coming. So it's like if that magnet is approaching the solenoid will say, don't come close. So it will push the magnet away. Then the second observation is, if a magnet moves away from a solenoid, the solenoid makes a magnetic field tending to attract it. So if you are pushing the magnet, you are intentionally pushing the magnet away from the solenoid is going to make a magnetic field that is going to say, you come close. So it's like when you want to bring it close, it's going to say keep away. If you want to keep it away, it will say come close. So then current flows according to their magnetic field. So remember, if you are moving a magnet towards a wire, or if you are moving a wire towards a magnet, current is introduced in the wire. So if you move a magnet towards a solenoid, current is going to be introduced in the solenoid. Okay, so that current will of course result in the creation of a magnet. So how is the magnet being created from the movement of the current? Remember how what we learned about how magnets are made using the electrical method. So if you put a soft magnetic material, then you put it around the solenoid, then you power the circuit. As long as current is flowing, that magnetic material is going to become a magnet. Okay, so maybe I bring in diagrams for you to comprehend. So before I do that, Lenz's law states that the direction of the induced current is the current that is introduced in the wire because of the movement of the magnet towards the wire. So the direction of the induced current is such that it produces a magnetic field that opposes the movement of the magnet inducing it. Okay, so it will become clear soon. So let's say we have this situation. So I've got a wire here. This wire is not connected to any kind of battery, so there's no power source. We just have a meter that measures the direction of the current and the presence of the current. So we have a solenoid here, and here we have a core. Okay, so remember what we learned in electrical method of making magnets. If you have a battery here and if current is passing, then of course this is going to become a magnet. You can predict where the north pole and the south pole is using Fermi's right hand rule. Okay, so let's say we have this, then we get a magnet. When you move the magnet towards this, what's going to happen is a magnet is going to be made such that this becomes a north pole, so that this north and this north, they repel, this magnet is pushed away. Okay, so that's one situation of Lenz's law. We are trying to bring them because this one is going to produce same keep away. Okay, so of course when you're moving this, what actually happens is current is produced in the wire, and this current which is introduced or which is induced in the wire is going to move in a direction such that it makes a magnet that has north here if this is north pole that's coming. Okay, so if you use Fermi's left hand rule, you can tell that the direction of the current is this, for this to be north. Okay, so let me just say that again. Using Fermi's right hand rule, you can tell where north is, okay, by the direction of the current. So in summary, what happens is you move this, as you are moving the magnet, current is going to be introduced, but the direction of the current is going to be such that this becomes a north pole, so that it repels this. If south pole is here, then this could have become a south pole, so that it repels this. Remember, like poles repel, as you are going to see in another example. Example 2. If you push the magnet inside the solenoid, no current is going to be to flow in here. That's a situation. Why? Because the magnet is not making any movement. So current only flows when the magnet is making some movement. Third is a situation where now you want to take your magnet away from the solenoid. Since you are taking the magnet away from the solenoid according to Lenz's law, then the magnetic field is going to be created such that this becomes the south pole and it will try to attract this north pole. So I want to take it away to say, no, come back, I want you. Okay, so even the current will be induced such that this is south and of course north will be away. The fourth situation, what if we did the same, but of course this time we have the south pole. So if you push the south pole towards the magnet, the south pole is going to be created here, so that this is pushed away. Okay, you want them to be close, it will say no, go away. And the opposite situation is when you want to take the magnet away, and if this is south pole, this is going to create north pole. So the job is to determine the direction of the current. Usually questions are structured such that you predict the direction of the current. How do you predict? If they give you south pole here and they have told you that the magnet was being withdrawn, then you have to know that according to Lenz's law, the magnetic field here is going to be such that it opposes this withdrawal. So it's going to be create a north pole so that these two attract. Okay, so once you know that this is going to be to create a north pole, then you use Fleming's right hand rule to determine the direction of the current. If north is here, then what should the current be? Okay, so that's the job. So now, how do we increase? Let's say we have seen that current is introduced in the wire. If you move a magnet across the wire, current is introduced in the wire, and that's how electricity is made. So if you want to have too much electricity, like a lot of electricity from this interaction, what can we do? So to increase the voltage or the induced current, you have to move the magnet at high speed. So you move the magnet at high speed, there will be a high current or high voltage. 2, you have to use a stronger magnet. 3, you have to increase the number of turns in the coil. So the turns that make the solenoid, you have to increase them for for a higher EMF or induced current to be there. So this is everything about electromagnetic effects. So this marks the end of part 2. It has been full of imaginative experiments. So we're doing experiments, the Fleming's left hand rule, and of course, hope you're able to follow, because I did not show all the possible orientation of the hand for you to predict the direction of the force, but I was just explaining, and you had to just imagine and try to do what I was saying. Anyway, this marks the end of part 2. Happy solving. Part 3 is going to be about applications of the concepts that we have learned here and in the first video.